All right, question 2 in the free response. We did so much calculus in the multiple choice that I thought I'd do a mechanics problem with energy and work where you didn't have to actually do a lot of calculus, just a little bit more physics. So we want to determine, so basically the situation is we have this mass hanging over a pulley. The pulley accelerates the mass and gets it moving. It accelerates the cart and gets it moving, and then we're plotting that we have this table of data that we're collecting from this force sensor and from and the motion detector. Took the speed, the force, and the speed squared. And we want to determine the average force exerted by the string. So what we're going to actually do is we're going to actually add these up. And so add and divide by 5, and we'll actually get 0.84 when you do that math. And then we want to do the average work done by the force. So since it's average work, we can actually treat everything like it's a constant. So we're going to get 0.84 times the distance over which it acts, which is 0.4 meters. And so we're going to end up getting 0.34 joules worth of work. Now, I've taken the liberty of plotting speed squared versus position, and this is the graph I got. And again, when they say draw the best fit line, draw a straight line. You don't touch all the points. You want to make sure that you've got some points above and below. And now what we want to do is we want to use this slope, sorry about that, to get the acceleration. So let's just remember v squared equals v naught squared plus 2a x minus x naught. In this case, x naught is 0. So what we're going to end up getting is v squared equals 2ax plus v naught squared. So our y-intercept, 0.33, is of course the v naught squared, and this is our y variable. That means the slope will give us 2a in this graph before. Rather than panicking, what I need you to do is actually read that sentence over, look at the graph, and we've got to get kind of on a thing where you're making the mental effort to make that connection yourself. I know that's kind of a harsh or cruel thing to say, but I think really I want to challenge you to forge those connections and not think to yourself, well, I didn't get it the first time, I'm never going to get it. But rather to sit with that for a little bit and see how we're able to arrive at that. Your hint, though, is, once again, since we've done a linear plot, this is y, m, x, and b, and the slope will be twice the acceleration. So let's get the slope from the best fit line. So we have m is y2 minus y1 over x2 minus x1. So let's see, this appears to be about, this is 0.2, so we'll make x2 equal to 0.2, and that's 0.7 right there. And then here, just for a lack of a better term, I guess this would be like what? Just to try to get some sort of number here. So that looks like it's about 0.7, and that looks like it's about 0.4 right there, because that's where it intercepts. So our slope is going to be 0.7 minus 0.4 divided by, and that's 0.07, sorry, 0.2 minus 0.07. So I'm getting 0.3 divided by 0.13. And so I'm going to get a slope of 2.3. And since that is twice the acceleration, I'm getting an acceleration of about 1.15 meters per second squared. According to the AP, the range they accepted was 0.83 all the way to 1.3. So just so you know. Now for part D, we're going to use a different method to calculate the work done. Let's use, since we know work is the change in kinetic energy, let's go ahead and use that. So I have 1/2 m v1 squared, v final squared minus 1/2 m v initial squared. So that's going to be 1/2 times m times 1.17 minus 1/2 times m times 0.33. I forgot to put that m is 0.65. Minus 1/2 times 0.65 times 0.33. And I'm going to get, roughly speaking, about 0.28 joules. So let's just figure out where. So we should have got, this is the work done, right? 0.34 joules by this pulling force. But it seems that the kinetic energy was only 0.28 joules of work done through kinetic energy. So it seems that the force didn't create only kinetic energy. I would argue that perhaps, if we want an explanation of why there's this discrepancy, I would say some energy was either one, dissipated by friction, or two, went into the wheel of the pulley. And I will actually label that on the previous page. This is what I mean by the wheel of the pulley. I think both those things might have taken away from the energy. So that's it for the second free response question, and I will put all this together in Haiku and push it out to you right now.